Hi, welcome to topic 2.4. This is Newton's first law. In the last video, we talked about Newton's third law, which was talking about for every action force, there's an equal but opposite reaction force. Here, it's gonna look similar to third law, but we're gonna focus on a couple things. Okay, we're gonna talk about equilibrium, which oftentimes questions may ask, like, what is a third law pair? What is a first law pair? And so they technically are probably the same physical force, but because when they get identified from one object to another, that's our difference between first and third law pairs. So what we're going to look at really is we're going to look at a net force, right? So the net force on a system, right, is the vector sum. So back in unit 1, we talked about vectors and how we add them and subtract them. So this is where it's really going to come into play again. So Newton's first law states that if a net force exerted on a system is 0, the velocity of that system will remain constant. So in the last unit, we talked about describing, and we kind of just, the duck on pond physics, we're above the water. Now we're going to go below the water. So what they're saying is if there is no net force exerted, then the velocity will not change. And then for this reason, we call this the law of equilibrium. Right, so the first law has two subheadings, right? So the first one is the law of equilibrium, and essentially equilibrium, balanced forces, right? And so essentially, if we remind ourselves of what constant velocity means, that means there's no acceleration. So in first law, objects are not being accelerated, okay? And you really have two types. You have static equilibrium when the object is not moving, and then you have what's called dynamic equilibrium, which is when the object is moving but not being accelerated. And that's oftentimes a misconception, that objects can't move or they don't move when they're not accelerated. Well, yeah, no, they move, just it'll be with constant velocity. Now, the second kind of name for Newton's first law is the law of inertia. So what is inertia? Is the tendency of an object to resist changes in motion. So funny picture there. So this is what happens when you brake on a bike or you hit something and you keep going forward, because your body wants to keep moving forward. But inertia says, no, I want to keep moving forward, but the bike's going to stay. And that's why you go head over the handlebars. Okay. Now, when we look at it, mass, all right, so our mass is the physical quantity associated with inertia. So large mass means high inertia, right? So the larger the mass, the more it is going to resist the change in motion. Small mass, right? Small inertia. Okay, so the smaller the mass, the easier it is to resist the change. Okay. So one area that you see this law of equilibrium are these tension problems, right? And so if I'm looking at this stoplight, I'm looking at this point right here, and if I draw those free body diagrams we talked about before, you have the weight of the stoplight down, and then this cable is split into two, right? So I have tension 1 and tension 2. And what happens is these tensions will have angles, right? And so you would have to split it up. And when we talked about vectors, right, ax, a cosine theta, ay equals a sine theta. And so you would, as you're summing the forces, you would do an x component, a y component. But the good thing is if the angles are, so no matter what the angles are, the x components of the tensions will cancel out. Okay, so they'll be equal but opposite, but it's the y components that are going to be different because the y side has this m times g in it. All right, so let's look at an example problem using these concepts with tension. And so a traffic light is supported by a cable shown below. The tension on cable 1 is 294.8. What is the tension in cable 2? and then what is the mass of the traffic light. Okay, so if we draw our free body diagram, you have traffic light down, which we don't know the mass. You have tension 1 at 25 degrees. And you don't have to write the angles on. I just like to do it so we kind of remind ourselves. Tension 2 is going to be at 15 degrees. Okay, so on the AP Physics 1 free response section, this would be your free body diagram. And then we kind of go from, now we sum the forces. So I like to do a T chart. So it'd say the sum of the forces in the y direction equals 0. The sum of the forces in the x direction equals 0. Again, we're in equilibrium, so we're not moving. All right, and then I do my, so I have T1x minus T2x equals 0, right? That's my vector sum. On this side, I have T1y plus T2y minus mg equals 0. And then I say T1x equals T2x. So T1 cosine theta 1 equals T2 cosine theta 2. And I just keep working my way down because this part will give us T2. So T1, so T2 equals T1 cosine theta 1 over cosine theta 2. And now I can plug in numbers. So 294.8 cosine 25 over cosine 15. And it gives us a tension of 276.6 newtons. Makes sense that it's less because the higher the angle, the more tension there is. Okay, now I go over to the y side and I need to start solving this for mass. So I get T1y plus T2y, and then mass is going to be T1y plus T2y over g. So T1 cosine theta. And so you can see these become essentially mathematically systems of equations, right? I need to solve one in terms of the other, okay? And now I can just do 294.8 cosine 25 plus, sorry, I always try to write over it instead of just erasing it. So 276.6, not cosine. These should be sines because that is our y direction. All right, I'm going to kind of move over here. So this tells me that the mass of my traffic light is about 20 kilograms. Okay, and then here was our tension 2. So what you could see here is the full process, right? We talked about it earlier. Draw, right? Sum, solve, right? So draw. These right here are sum steps, and then anything below this is our solve. In fact, the way you can think about it is this up here above it is physics. Below that line is math. Okay, so what you can see here is that full process of draw, sum, solve. And as we get going, especially when we talk about Newton's second law, we're just going to keep adding to this problem solving process.